In this video, we're going to talk about solutions and other kinds of mixtures. We're going to classify solutions in different ways by particle size, by concentration, and by whether the particles are truly dissolved or not. First, we'll start off with the level of concentration. There are three levels of concentration. Unsaturated is the least concentrated, saturated, and then supersaturated. So what does it mean? To be unsaturated means that the solvent is holding less solute than it is technically capable of holding at a given temperature. There's a limit to how much solute you can dissolve in a solvent. And that limit is temperature dependent. So generally speaking, at higher temperatures, you can usually dissolve more solute for most compounds, although not all. You can usually dissolve more solute per unit of solvent. At cooler temperatures, things tend not to be as soluble. The typical example is table salt. We think of table salt as being just almost infinitely dissolvable or soluble in water, but the truth is table salt is one of the least soluble ionic compounds in water. We just don't realize that because we never try to dissolve that much salt in water. At room temperature, you can only dissolve about maximum 36 grams, maybe 36.5 grams of table salt, sodium chloride, into 100 milliliters of water. That's not a tremendous amount. I think that works out to about 20 to 25%. That's the maximum. At that point, you've saturated your solution. Anything less than saturated is unsaturated. So if you dissolve less than 36 grams of table salt into 100 milliliters of water, then you have an unsaturated solution. That means if you add any more salt, that extra salt that you add will dissolve up until you've reached 36 grams per 100 milliliters. If you try to go over that, what'll happen? Well, if you try to exceed the limit, it just won't dissolve. You can reach the point where if you try to dissolve, say, 50 grams of sodium chloride into 100 milliliters of water, some of it will dissolve, but the excess, the extra 16 grams that you try to dissolve above, or 14 grams that you try to dissolve above and beyond 36, so 50 minus 36, that's where I'm getting 14 in case you're wondering. If we try, just hypothetically speaking, if we tried to dissolve 50 grams of salt into 100 milliliters of water, 14 grams of that would remain undissolved salt crystals, and they would simply sink to the very bottom of the bottle or glass or beaker of water, undissolved. The water would not be able to dissolve those extra 14 grams, and they would remain undissolved. That's how you know you've reached the saturation point. You cannot dissolve any more of your salt, any more of your ionic compound or your molecular compound. Now, at a temperature of about 90 degrees Celsius, you can dissolve up to 40 grams maximum of salt. So at room temperature, 36 grams of salt is the maximum. At 90 degrees Celsius, at very hot temperatures, you can actually dissolve up to about 40 grams of table salt. That's the limit. So your saturation point isn't until you get to 40 grams of salt dissolved in 100 milliliters of water at 90 degrees. So it's temperature dependent. Different temperatures will have different ranges of dissolved solute for the unsaturated, saturated, and supersaturated tiers or levels. So a saturated solution is a single point. It's a single point at which, at a given temperature, the solution is holding exactly the maximum amount of solute for the given temperature, obviously. So the example would be a brine solution. A common example might be sodium chloride that has exactly 36 grams or 36.5 grams dissolved in 100 milliliters of water. You can't add any more salts that will, well, at least not expecting it to dissolve. And if you add any less, it would be unsaturated. Any more wouldn't generate a saturated, you can't just make a saturated solution by shoving more solute into the solvent, right? That it doesn't work that way. The solvent doesn't cooperate. It doesn't dissolve the extra solute you add. So you might wonder, well, then how in the world do you get a supersaturated solution if you can't do it that way? Well, there are ways. And we'll talk about those ways. You probably already got a hint that you can oftentimes dissolve more more solute at a different temperature. So what you can do is you can change the temperature, add more solute, dissolve more solute in your solvent, and then slowly and carefully change the temperature back to the temperature you wanted. And if you do it slowly and carefully, the solution will not, I hate to make it sound like this, but it's the only way I can really describe it. The solution won't realize you have tricked it into holding more solute than it really can hold. You've tricked the solvent into dissolving more solute than it can hold at a given temperature by changing the temperature, putting in the extra solute, and then changing the temperature back. Now, the solvent will realize this at some point. If you give it enough energy, if you shake it, disturb it, or if you add something called a seed crystal, the solvent will sort of wake up and realize, hey, I've been duped into dissolving more solute than I should, and it will suddenly recrystallize all the solute. All the solute will come, quote unquote, crashing out of solution and become a solid all at once. Because it's an energetically unfavorable position for a solvent to hold more solute at a given temperature than the saturation point. And so it'll realize that, and it will fix that state by kicking all of the dissolved solute particles out of solution, almost literally kicking them out. This is actually referred to as crashing out. The solute particles crash out. They recrystallize. That's another word for it. The more formal term is to say they recrystallize. The solute particles form a solid that is no longer dissolved in the solvent. But you have to do this slowly and carefully. Otherwise, if you don't, then it never happens. You never get your supersaturated solution. Automatically, the solute particles just sort of recrystallize before you're ready. Now, why might someone want to do this? The reason they might want to do this is to get these nice little rock candies and rock salts and other crystals, larger crystals than you normally would see. So recrystallization is the process of a solute crashing out of solution due to supersaturation, actually due to the effects of correcting for the supersaturation. So recrystallization is the sudden formation of a solid from dissolved ions in a supersaturated solution. The supersaturated solution, like I said, is an energetically unstable situation. It cannot last indefinitely. Eventually, something is going to disturb this system. It's going to give these dissolved solute particles enough energy to reconfigure themselves into a more stable arrangement. And that more stable arrangement is for them to leave solution, meaning to become solidified, and so that they are no longer dissolved in solution. This is called crashing out. That's the terminology we already used. That's how you get these nice big crystals of sugar when you have sugar candies. The color, by the way, just comes from food dye. It's not something innate to the crystal colors themselves. Sugar, of course, is clear or white. Sugar crystals are clear or white. They don't suddenly develop color because they're being recrystallized. That's food dye. That's just dye. Salt does the same thing. You can get very large crystals of salt from doing the same kind of thing. You heat up a solution, you add a lot of salt crystal or sugar to the solution, you dissolve all this extra salt, extra sugar, then you slowly cool it down. As you cool it down, you can prevent it from recrystallizing by being careful not to jar it or somehow bump into the vessel that holds your supersaturated solution, and it'll simply remain that way. And then when it's time to actually form the recrystallized product, you actually can add what's called a seed crystal. A seed crystal is a tiny, tiny crystal of whatever it is you're trying to form. If it's salt, then it's a tiny, tiny piece of salt. If it's sugar, then it's a tiny, tiny crystal of sugar. And it doesn't have to be large at all. In fact, it could be the size of a pin, the sharp end of a pin. That's how small it can be. All you need, and all the dissolved particles need to see in a supersaturated solution, is some kind of crystal lattice that they will jump onto and add to and build onto. So the seed crystal is what's called a nucleating center. What it means is, what it is, a nucleating center is just a platform, a sort of pre-established lattice upon which all the positive and negative ions can jump onto. So the negative ions, in a sodium crystal, a sodium chloride crystal example, the chloride ions will see the sodium ions in the seed crystal, the lattice, and the chloride ions will be attracted to the sodiums. Sodium ions that were dissolved in the supersaturated solution will see the chloride ions that are in the lattice and will jump onto them, and they will automatically form those beautiful crystal lattices that we've looked at before, those pictures of, green and gray interlaced spheres that make up the lattice. And so they will automatically build out that pattern. They will continue the pattern. And as more and more dissolved solute particles join the lattice grows and becomes a full-on solid. And you can actually see, and I'm not going to play the video here because it'll end up being choppy, but watch this video. You can either watch the video. You can either watch the video. Oh, I'm sorry. I seem to have made a choice that I didn't want to make. Okay, let me try that again. I'm sorry, it's kicking me out for some reason. Here, let me try that again. Okay. We are. I don't know why it's doing that, but okay. All right, let's try that again. I'm not going to be able to play this video because, well, I can, but it'll be very choppy. But go ahead and watch it. It's like a 2-minute video. And you can already kind of see here that the crystalline lattice is forming in this otherwise. The solution starts out clear and colorless. But as right after the person puts a tiny seed crystal to get the process started, that seed crystal grows into this solid white crystal here. This is sodium acetate trihydrate. It's a supersaturated solution. It starts out as a supersaturated solution. Of course, at the end, it's no longer supersaturated because, remember, solids inside of liquid, if they are not dissolved, if you can see the solid, it's not dissolved. So it's not technically part of a solution anymore. At the end, you have a heterogeneous mixture. The solution itself is no longer supersaturated, but is then just either saturated or even possibly unsaturated, depending on the level of concentration of the solute. Because as the solute particles leave the solution and become solidified, part of the solid, they are no longer part of the concentration of the solution. So the recrystallization process takes place automatically once you add a seed crystal. Sometimes you can also just sort of knock on the glass vessel, and that'll provide enough energy to get the process started, to get all those dissolved solute particles to form together, to band together to create a solid and to leave the solution. Remember, a solid inside of a liquid is not a solution. This crystal, these solid particles here are not part of the solution. They are not dissolved. And if anything is not dissolved, it's not really part of the solution. Just because they happen to inhabit the same volume of space doesn't mean that there's a true solution there. That's just a heterogeneous mixture. A solution, remember, is a homogeneous mixture. This process, by the way, you can't tell from looking at the video, but it is exothermic. If you were to put your hands on this glass round bottom flask here while this process is occurring, you would feel the glass getting warmer. This is giving off heat. That's because all the energy that was this high energy situation of having a supersaturated solution, all that energy is given back as these crystals form and the solute particles stabilize into a solid. So all that energy is given back and given off to the surroundings. So if you touch this glass, it'll feel a little bit warm. It's an exothermic process because you're going from an unstable state, high energy, to a more stable state, less energy. The excess energy has to be given somewhere. It's given out to the surroundings. If you're touching the glass, you're part of the surroundings that's receiving that heat, that thermal energy. Oh, shoot, I started accidentally. I still don't know how to control this way. I'm using a different device today, so I'm a little unused to the way it gets controlled. All right. Okay. All it does is it seems to just want to start the video, but you watch the video. It's only 2 minutes. It's pretty neat. It's nice to look at, and you can see lots of videos like that. Temperature versus solubility. Now, for most ionic compounds, by no means all. In fact, many of the most common ionic compounds. This is true for many of the most common ionic compounds, but by no means all. As you raise the temperature, dissolve faster, and you can dissolve more of the ionic compound per given amount of solvent. We're going to mainly just look at water as the solvent in this case. If you look at this picture over here, this graph here, this shows the solubility of different kinds of ionic solutes per 100 grams of water. Remember, the density of water is more or less 1 gram per milliliter. I mean, technically at 4 degrees Celsius, that's exactly 1 gram per milliliter. Any warmer temperature, the density of water actually decreases slightly, but don't worry too much. For our purposes, 100 grams of water is 100 milliliters of water, rounded to the nearest worthwhile significant figure. So grams of salt, by the way, meaning any ionic compound, grams of ionic compound per 100 milliliters or 100 grams of water. This is not a percentage. All right, so let's make that clear. This is grams per 100 grams. You can turn this into a percentage, but this isn't a percentage necessarily. You'd have to do some calculating, and we are actually going to do that calculating here. This is sort of a rehash of the whole percent by mass calculation. We'll practice doing that here. Notice most of these, as temperature increases, for most of these compounds, as temperature increases, the amount of grams, the solubility also increases. Almost all of these have positive slopes, except for one. Which one does not have a positive slope? Which compound actually decreases in solubility as temperature increases? That's right, it's cerium sulfate. I'm going to assume you said that. So this is the only one, cerium sulfate. Ce is the lanthanide cerium. It's one of the F block elements. Cerium sulfate or cerium 3 sulfate, its solubility actually decreases with increasing temperature. It's not the only one though. I believe calcium hydroxide and I think maybe even aluminum hydroxide are flipped, meaning as you increase the temperature, their solubility in water decreases. But don't take my word for it. And I don't have it. I don't have the graph here and I don't have the information in front of me, but I believe calcium hydroxide and aluminum hydroxide, like cerium, cerium sulfate would have a negative slope, meaning higher temperature results in lower solubility. But for most of these, as you increase temperature, they not only dissolve faster, but they dissolve more. So look at sodium chloride. Sodium chloride, by the way, if you notice, is one of the ones that is one of the lesser soluble salts, especially at high temperature. Virtually, other than cerium sulfate, virtually every other compound here has better solubility in water, at least beyond the 80 degrees Celsius range, 85 degrees Celsius range, than sodium chloride does. And sodium chloride doesn't even start off that great. In fact, the temperature effect for sodium chloride really only results in about a 10% increase in solubility from a maximum 40 grams down to a minimum of about 35 grams. So it's only a 5 gram per 100 milliliter of water difference between its lowest solubility and its highest solubility. So across the entire temperature range of water, where water is a liquid from 0 degrees Celsius to 100 degrees Celsius, sodium chloride really doesn't change its solubility that much. On the other hand, you have things like calcium, you have components like potassium dichromate, which, in very, very cold water, you have very little potassium dichromate, K2Cr2O7 dissolving. But then as you raise the temperature of water, you go from about 5 grams of potassium dichromate all the way up to about 80 grams. That's a 16-fold increase, 16 times increase in the amount of potassium dichromate that will dissolve in water. Likewise with calcium, you see this exponential increase in the amount of calcium chloride that will dissolve in water with just a small increase in temperature. So different compounds have different solubilities at different temperatures. Most compounds, as you can see, have positive slopes. So most of their solubilities improve in water anyway, with increasing temperature, except for cerium sulfate. So cerium sulfate becomes less. Oh, I guess I didn't really. Well, either one, cerium 2 sulfate or cerium 3 sulfate, either one is probably the same scenario, becomes less soluble in water. Okay. Think about this question, by the way. 36 grams of sodium chloride per 100 milliliters of water. This is the saturation point at room temp, or about 25 degrees Celsius at room temperature. If you look at the graph, 25 degrees Celsius right here, if you look at this graph at 25 degrees Celsius and you trace a straight line vertically to sodium chloride, you'll see that you're dissolving about 35 grams or so. It's right in between the 30 and the 40 gram mark. So you're dissolving about 35 or 36 grams of sodium chloride per 100 grams of H2O. Remember, the vertical axis here, the y-axis, I guess, does not represent percent. It represents grams of salt for every 100 grams of water. But a percent is not grams of solute per grams of solvent. A percent is grams of solute per the sum of the grams of solute and solvent. So what is the percentage? Well, if you have 36 grams of sodium chloride per 100 milliliters of water or 100 grams of water, can you tell me the percent by mass and the molarity of a saturated sodium chloride solution? So a saturated chloride solution, a saturated solution is anything for any one of these compounds is anything along these lines at the given temperature. So at a temperature of 25, you're on the line at 36 grams. At 25 degrees Celsius, a saturated potassium dichromate solution would be about 13 grams, 13 or 14 grams, because you'd be right on the line. Wherever the line is, that represents the saturation point for that given temperature. So what would it be? What's the percent by mass or percent by weight of a saturated sodium chloride solution? Don't be so quick to say 36%, right? It's not. That's not the answer. What is it? Well, let me use a different color. Let's go with dark blue. So at this point, you'd have 36 grams of sodium chloride dissolved in 100 grams of water. That would give you a percent that is 36 grams of solute over 100 grams of water of the solvent plus 36 grams of sodium chloride together. And of course, because it's a percentage, you multiply by 100. So the percentage by mass or by weight would be 36 divided by 136. Not 36 divided by 100, 36 divided by 136. And that would be about, and this is a saturated table salt or salt solution, 26.5% NaCl. That would be a saturation. At room temperature, that's your saturated solution. At 25 degrees Celsius or room temperature. What would that be in molarity? Well, molarity, you would take the 36 grams and you would divide it by 58.5 to get moles, grams per mole. That's the molar mass for sodium chloride, 23 plus 35.5 grams per mole. You take your moles, you take your grams, convert to moles, and the bottom is 100 milliliters, right? 100 grams is 100 milliliters. That's 0.1 liters of solution. Remember, when it comes to solids, we don't bother trying to figure out the effect that solids have on solution. We just take the water or the volume of our solvent as our volume. So our molarity is going to be our grams converted to moles divided by our milliliters converted to liters. So we take our 36 divided by 58.5 grams. That gives us moles. divided by 0.1 liters, because we have 100 milliliters by definition of solution here, of water, which we're going to assume is our entire solution volume. And we get a approximately 6.2 molar concentration. So 26.5% by weight sodium chloride is equivalent to 6.2 molar sodium chloride solution. So that's the answer to that self-test. So that's your self-test. Can you tell me, and I hope you can, the molarity and the percent of a saturated sodium chloride solution? Saturation comes from looking at room temperature. And remember, the saturation point is different for different temperatures, but following 25 degrees Celsius, if I draw a line as best as I can straight up, that takes me to this point on the sodium chloride graph, which is approximately halfway between 30 and 40. I'll just tell you it's actually 36, only because I know that, not because I'm very good at parsing lines on poorly drawn graphs or low resolution graphs. It's only because I know that. But if you guess 35, you'd be close enough. It's roughly halfway between 30 and the 40 mark, 30 grams and 40 grams per 100 milliliters of water, or 100 grams of water. So hopefully that makes some kind of sense. Okay, let's take a look at this graph. Now I blew up this image a little bit, or actually all I did was zoom in. And we're going to do a few questions here. This is the most, math intensive part of this. A lot of it has to do with reading graphs and making calculations. Okay. For some reason, I didn't end up putting that point where I wanted to put it. Oh, well. Okay, well, what is the percent? Let's do another one now. What is the percent by weight of a saturated, and remember, saturated means exactly on the graph at a given temperature, of a saturated calcium chloride solution at room temperature? Remember, room temperature is 25 degrees Celsius. So if I look at this, and I look at room temperature, and let's see, sorry, I'm just going to see if I can use a ruler to help me along here. If I can find a small enough ruler. No, of course not. It disappeared. I had one right here on my desk, and now it's gone. Where did it go? I have no idea. Okay, well, I'm just going to have to freehand this after all. I was hoping to do a little better. Okay, so 25, sorry about that, 25 degrees Celsius, calcium chloride at room temperature. So we draw a straight line from 25 degrees Celsius. We try our best, and I'm going to have a hard time doing this because I'm drawing vertically or sideways. I'm going to draw a straight line up to calcium chloride. Right through the middle here, wherever it lands. Oh, look at that. So I'm just going to take this point right here, right at this point. So what is that? That's 90 grams. So if I trace the line from 25 degrees Celsius up to the point where it intersects the calcium chloride graph, and then I draw a straight horizontal line to what it says on the left side, I get 90 grams per 100 milliliters. So that's 90 grams of calcium chloride dissolved at saturation. That means I have 90 grams dissolved in 100 grams of water. Now, you're going to be tempted to think, oh, okay, well, that's 90%, but it's not. Remember, that's 100 grams of water. That's not 100 grams of solution. Remember, the mass of the solution is the sum of the mass of the solute and the mass of the solvent. Keep that in mind. It's so easy to forget that. So the mass of the solution, the denominator in our percentage, our percent then, by weight or by mass, or however you want to say it, is going to equal I have the hardest time writing. Sorry, I am writing sideways. It's almost impossible, sorry, to write straight. 100 grams of water, that's our solvent, plus 90 grams of solute. That is the mass of our total solution, mass of solution. The percent by mass is always given over the mass of the solution. So, and we have 90 grams of calcium chloride on top. So we have the part divided by the whole. Calcium chloride is the part, and then the whole includes the part plus the remainder. So 90, we get 90 divided by 190 times 100. That's going to be a little bit under 50%. So let me just work that out. I don't trust myself with math anymore, so I'm just going to use my calculator every single time, no matter how simple. 47.4% is what I get. That, oh God, sorry about that. This thing responds to every little touch. It's a different machine, so I'm really not used to doing this. 47.4% calcium chloride is the percent by weight, of our saturated calcium chloride solution. Notice that if we were at a different temperature, we would have at a different saturation point. So for example, at 5 degrees Celsius, and this is not the question now, but at 5 degrees Celsius, our saturation point would have been 60 grams per 100 milliliters. And that would have been 60 divided by 160. And that would have been, I don't know, whatever 60 divided by 160 is, I guess, 37.5% calcium chloride by weight. We would have had a lower percent by mass solution at saturation because we have less that's able to dissolve. So that's how you do it. I'm just going to erase this now because that really wasn't the question, right? Our question was, it's not erasing. Go figure. Nothing ever works. Okay. All right. Well, I tried. 47.4% calcium chloride. So that's how you get that. That's how you read the graphs. But let's continue on. Let's do some more examples. We're going to do about 4 more examples. We're just going to practice reading the graph and understanding the relationship between temperature and solubility, and between saturated versus unsaturated versus supersaturated. Okay, here's a question. Here's another concept check question. Is my 50% by weight potassium nitrate, and here's our potassium nitrate, that's the green graph, if you can see it, or KNO3, they're labeled. Is my 50% by mass potassium nitrate solution unsaturated, saturated, or supersaturated at 40 degrees? Remember, you need the temperature. You can't just look at the graph and make a decision. You have to intersect it. You have to get a specific temperature and watch where it intersects the graph. So at 40 degrees, I'm going to use green just because the graph itself is green. So at 40 degrees Celsius, I trace that line of 40 degrees Celsius up to the point where it intersects my potassium nitrate graph, and that's right about there. So depending on how you read the graph, and of course, we're not all going to read it exactly the same, but within reason, I think most of us will agree this is somewhere between 63 and 64. You might say 62, that's fine. You might say 65. I would disagree. I think it's a little bit before the halfway point. So going from 60 to 70, I'd say this is less than halfway. I'm going to just go ahead and say this is 64 grams. If you want to say 63, I'm on board with you there too. If you want to say 65, I might dispute that, but it's within reason. So let's say 64. I'm going to say 64 grams. But your reading is probably as good as mine in this regard. So 64 grams of potassium nitrate gets us saturation. So the question is, how does my 50% compare to the 64 grams? Well, I can do this one of 2 ways. I can either convert my 50% by weight into a relationship between, and you know what, let's do it both ways. I can convert that to the same kind of ratio of grams of salt to grams of water. I can convert the 50% to that, or I can convert my 64 grams to 100 grams of water ratio into a percent. Either way, I have to compare my numbers by converting from one expression of concentration into another, from a ratio to a percentage, or from a percentage into a ratio. Let's do it both ways and see if we get the same sort of comparison. So the first method I'm going to use is I'm going to go ahead and convert my ratio of 64 grams to 100 grams into a percentage. What does that mean? That means I have 64 grams of potassium nitrate divided by what? Not 100, but 100 grams plus 64 grams. Remember, part divided by whole. It's never just part divided by the other part. It's part divided by two parts, including the part on the bottom. So 100 grams plus 64 grams times 100, that's my percent. So I'm converting the ratio I get from here. Remember, look at the units here. The units are not a percentage. They are a ratio of solute to solvent. That is not a percentage. I need to make sure I convert this into a percentage by doing this. So I take 64 divided by 164, and I get 39%, almost exactly 39%. 39.0% KNO3. Okay, so my question now is, now that I have these two numbers to compare, is 50%, this is by mass, this is my percent by weight now. So now I can compare these straight up by number. Is 39%, what does this tell me? Is my 50% solution saturated, unsaturated, or supersaturated? How does 50% compare to 39%? Well, 50% is clearly a greater number, right? 50% by mass is greater than 39% by mass. Therefore, this solution has a greater concentration than saturation. Remember, if I'm reading it right off of the graph, that indicates a point of saturation. 50% then is greater than my solution of 50% is above saturation. The saturation point specifically at 40 degrees. Now, it doesn't mean it has to be that way, right? I mean, if we were at a different temperature, I might be able to dissolve more, but right now I'm above saturation at the 40 degrees Celsius mark, meaning my solution is what? Well, it's not saturated if it's above, right? Anything above the graph represents what? Super saturated. Therefore, these three dots, by the way, mean therefore, I think I've said that before. Therefore, my solution is super saturated. It's got more solute dissolved in it at 40 degrees Celsius than it can technically hold. That's my answer there. Super saturated. It's above the graph at that temperature. Anything above the graph, anything above any given graph is supersaturated at a given temperature. Anything below the graph is unsaturated, and the graph represents all the saturation or all the saturation ratios for every single temperature. So I'm at 39%. I'm sorry, I'm at 50%. Let's do it the other way now. Let's check this the other way. Let me change my color here. Okay, let me draw a line here. And let's do method 2 now. Let's instead, because I want to show this to you both ways. So now we converted the 64, the grams, into a percentage. Let's convert the percentage into a ratio. What does 50% by weight mean? 50% means 50 grams of KNO3 per 100 grams, not of water, but of solution. Remember that solution is on the bottom, not individual solvent, times 100. That's what this equals. When we say 50%, this is what we are saying. Okay, Well, what does that imply? If we have 100 grams of solution, and we know the solution is solvent plus solute, what doesn't that really just mean that we have 50 grams of KNO3 for every 50 grams of KNO3 plus how many grams of water? Well, if we have 50 grams of KNO3 in our solution and the total is 100, then it must be, through the process of elimination, it must be 50 grams of H2O, right? 50 grams of H2O. So what we have is 50 grams of potassium nitrate for every 50 grams of water. Now, over here, it tells us that every 100 grams of water will allow us to dissolve up to 64 grams. Well, if we had, instead of 50 grams of water, what if we had 100 grams of water? So what this is telling us is that we have a ratio of 50 grams of KNO3 to every 50 grams of water. What if we had 100 grams of water? Well, 100 grams of, if 50 grams of water of KNO3 equals 50 grams of water, 100 grams of water, therefore, should give us what? 100 grams. Since it's a one-to-one ratio, of solute to solvent, 100 grams of water would give us 100 grams of potassium nitrate. So we would be up here. At this point, we would be way up here at 100 grams. Clearly supersaturated, right? Clearly well above our point of saturation. We'd be way up here. On the graph. That's where our point would be on the graph. What temperature would we have to reach in order to actually dissolve that much potassium nitrate in 100 grams of water? That's actually not the question, but this still tells us supersaturated because we're way above the graph. Supersaturated. Can you tell? Can you tell what temperature we would have to reach in order for this supersaturated solution to not be supersaturated? In other words, how warm do we have to get this solution? To what temperature do we have to warm up the solution in order to dissolve all 100 grams of potassium nitrate? Well, let's just follow the graph. Follow the graph. So we keep going, following the graph, all the way till we get to the 100 grams of potassium nitrate mark. That would be right here. The graph ends here. So this is the point. And at this temperature, let's see, that's about halfway between 50 and 60. I'm just going to call it for 55 degrees. It might be a little under, but 55 degrees Celsius. In other words, we'd have to heat this solution up another 15 degrees Celsius, up to from 40 to 55 degrees Celsius, in order to make sure that potassium nitrate completely dissolves. Otherwise, we're going to have some undissolved potassium nitrate just floating, or not floating, but sinking down at the bottom of our beaker full of water and potassium nitrate solution. So I hope you can see that. If this point here, this point here for potassium nitrate represents supersaturated at 40 degrees, if we simply move over to a hotter temperature, we see that the graph of potassium nitrate intersects the 100 grams of potassium nitrate dissolved in 100 grams of water line. That's right here and if you trace that line straight down, you'll draw a straighter line than me, you'll get to 55 degrees Celsius. So at the 55 degrees Celsius mark, that's when our solution goes from supersaturated, our 50% solution goes from supersaturated to plain old saturated, and all of that potassium nitrate will dissolve. All 64 grams of that potassium nitrate will dissolve. Or sorry, not 60. All 50 grams will dissolve, or 100 grams, or whatever it happens to be. By the way, the percentage doesn't tell us exactly how many grams we have. We could have, we could have 1 gram of solute for every 2 grams of solution. We really don't know how much we have. But the point is, at that level of concentration, we'll have achieved our, we'll have, at that level of concentration, we'd have to reach 55 degrees Celsius in order to dissolve it all. Hope that all made sense. So we just did it two different ways. Method one, so one method, no real preference. It's really up to you which way you want to do this. Method one, method number two. Either convert your percent to a ratio or convert your ratio to a percentage. Either way, you need to be able to compare these levels of concentration, these expressions of concentration directly to each other so that you can figure it out. Okay, let's go to the next question. Now, originally I had intended for this point A not to be there. Well, originally I intended to be right where it is, but then I changed it. And then I guess for somehow my old graph got resubstituted back in. So I guess we'll answer this question for two different points, maybe. Point A, and then we'll do the question for point B. Okay, so point A is right here. You can see it right here. List all solutes for which point A is unsaturated. So point A is sitting right on the potassium chlorate graph, KClO3. So clearly, if it's on a graph, that particular solute cannot be unsaturated, right? Because the graph itself represents the point of exact saturation. It's one point. The line that these graphs trace out are the saturation points at every single temperature. So KClO3, for example, we don't have to start with unsaturated. Saturated, there's only one solute that is saturated, and that is the KClO3. KClO3. Point A is right on the KClO3 line. Does everyone see that? Remember, these graphs are graphs that represent saturation for a given temperature. Now, what does unsaturation mean? Unsaturated means any point at a given temperature below the graph. So which graphs, in other words, the answer to this question for unsaturated is which graphs are above point A at the temperature approximately 75. So if we draw a line 75 at 75 degrees Celsius, and we just draw a line straight up, every graph that is sitting above A, every graph that passes above A is going to be unsaturated. All those solutes are unsaturated at that concentration level. Remember, the fact that I put point A on KClO3 doesn't mean point A is somehow tied to KClO3. It is not. Point A simply represents a point at which you have a 75 degrees Celsius solution and a what is that? About a 33 gram solute, and it doesn't matter what the solute is. I mean, it matters, but what I'm saying is I'm not tying the solute to KClO3. All A represents is a specific combination of temperature and solute per 100 grams of water, solute concentration or solute ratio. That's all it represents. Point A has nothing, is not somehow linked to KClO3. It just happened to be on KClO3 because KClO3 goes through that point. I could have picked A to be anywhere, any random location on this graph. I happened to pick KClO3 because I want at least one of the answers to be exactly saturated. Otherwise, if point A were not located on any graph, then saturated would be 0. There'd be no answer for it. It'd only be a combination of unsaturated or supersaturated solutions. Okay, so any point above A along this line, any one of these graphs represents a solute, including the graphs that aren't even on the, including the plotted lines that aren't on the graph. Remember, if these lines keep going up, they are also above point A. Clearly, these are all above point A. So almost every single one of these solutes would be unsaturated at 33 grams for every 100 milliliters of water. So let's just start from the top. So unsaturated would be sodium nitrate for point A. Sodium nitrate, calcium chloride, lead nitrate, potassium nitrate, almost all of them. That's why I didn't want this. I wanted to put this point further up, but well, vagaries of PowerPoint, undoing what I do. Potassium dichromate. God, there are too many. Cr2O7. What else? What other graphs? I made a kind of a mess here. Hold on. Potassium dichromate, KCl. All of these plots pass above the A point. That means each one of these could have had this much more solute dissolved in the solution at the temperature of 75 degrees, and before reaching saturation. So they are all unsaturated. NaCl. Of course, now it looks like all of these are referring to point B. They are not. We are still doing point A. I'll put in a point B later. NaCl, what else? What else is it? That's it, right? I think we got all the graphs. KClO3 is saturated. How about supersaturated? What would be supersaturated at 75 degrees Celsius with 33 grams of that particular solute dissolved in 100 grams of water? Well, there's only one graph that sits below point A at 75 degrees Celsius, and that's the cerium sulfate. So that point is below. So that's supersat. At 75 degrees Celsius, trying to dissolve 33 grams of cerium sulfate into 100 grams of water, in other words, this level of concentration would represent a supersaturated cerium 3 sulfate solution. Supersaturated cerium sulfate solution. Can you say that 5 times fast? Okay. That's for point A. And just in case I've made it totally unclear, let me just erase all this other stuff. There is our point A. So anything above a certain point, any graph that is located above a certain point means that that point represents an unsaturated point. In other words, below each one of these graphs, so for example, sodium nitrate, anything below the graph at any given temperature represents unsaturated. Anything above the graph represents supersaturated, and everything on the graph represents saturated. That's how it works. Anything above the graph represents a concentration that is above the saturation point. Anything below the graph represents a number of grams that is below saturation. And you can do that for each one of these graphs at every given temperature, or any given temperature. Let's do a different point. Let's do now point B. I'm going to put a point B up here, and let's see if we can figure that one out, which is what my original intention was. My original intention was actually to put point B right about here. And let's just read to the nearest line. Let's make our lives a little bit easier in this way. Okay, so let's make this point B. Okay, so I'm adding to this problem. Okay, I'm creating another problem. It's not necessarily on the PowerPoint right now. I'll see if I want to add it later officially, but right now I'm just extemporaneously making up another point to analyze. So now let's do point B. Okay, let's do the easy ones first. Point B, at point B, clearly there are two compounds that are, and let's just interpret them as hitting the same point here. In case there's any doubt in your mind, let's do this right there, right where these two intersect that point. At point B, both potassium nitrate, the plot for potassium nitrate and the plot for lead nitrate pass right through point B at the same point. So both of them are saturated. Point B lies on both plots, on both graphs, the one for lead nitrate and the one for potassium nitrate at that temperature, at a temperature of approximately 49 degrees Celsius, just before 50. So hopefully you see that. Both lead nitrate and potassium nitrate intersect point B, so they are both saturated at that point. Now, which solutes are unsaturated? So at 49 degrees Celsius, right before the 50 line, we have cerium sulfate, of course. We have all these other graphs, which at 49 degrees lie below point B. So KCl is going to be unsaturated at that level. No, wait. Oh, I'm sorry. Wait, I've got this backwards. Excuse me. Sorry. Supersaturated. Sorry. Point B lies above all these graphs. Sorry. Anything above these graphs. So KCl is going to be supersaturated because point B lies above the KCl level. So at 49 degrees, saturation is represented by about 41 grams. But point B represents about 85 grams. So 85 grams is definitely way more grams than KCl can handle at 49 degrees. So KCl, point B is above KCl, point B is above NaCl. Point B is also above potassium dichromate. Oops. Potassium dichromate. Here we go. Potassium dichromate. What else? I said NaCl, KCl, KClO3, potassium chlorate. And finally, of course, cerium being one of the least soluble compounds, especially at higher temperatures. You know, cerium sulfate is also going to be supersaturated at that temperature with that combination. Remember, point B is not inextricably tied to potassium nitrate or lead nitrate. No, point B simply represents a combination of temperature and concentration. Concentration expressed in terms of a ratio of grams of whatever solute you're talking about per 100 grams of water. So I would say point B, to the best of my reading, would represent 49 degrees Celsius, comma. To me, this represents almost exactly 85 grams of solute. Per 100 grams of water. In other words, concentration, some form of expressing concentration. So at that level of concentration and at that temperature, if we tried to apply that same concentration or tried to get that same concentration of potassium chloride or sodium chloride or potassium chlorate or cerium sulfate, we would have supersaturated solutions of those particular compounds. Now, what's above that? Well, above that, even though you can't see it, you can pretty much assume that sodium nitrate is going to keep going up, and you can assume that calcium chloride is going to keep rising as well. So you can assume both of these compounds are unsaturated at that point because their graphs presumably pass above point B. So sodium nitrate would be unsaturated, and so would calcium chloride at that concentration of 85 grams. So that would be for point B. So we have point A we looked at and point B we also looked at. Okay, let's go on to the next question, next concept check. I still have point A there, but we're not going to make any more use out of it. What is the maximum number of grams of cerium sulfate? So that's cerium sulfate down here. What is the maximum number of grams of cerium sulfate I can dissolve in 250 milliliters of water at 18 degrees Celsius? 18 degrees Celsius. So 18 is going to be right around here, just a little bit before 20. I'm going to draw a straight line to my cerium graph, which is this kind of burgundy graph. It's the only graph that's downward sloping, right? So right about here. This is the point right there. Okay, so at that point, maximum number of grams of cerium sulfate I can dissolve in 250 milliliters. Now be careful here. According to the graph, how much cerium sulfate can we dissolve in 100 milliliters of water? Well, if we read off of the graph at this point, I'm just going to trace a line straight to the left-hand side. From that point, I follow my temperature of 18 degrees up to the graph, and then I draw a straight line to the left-hand axis. And that tells me What is that? That's about right between 0 and 10. So I'm going to say about 5 grams, right? That point represents about 5 grams of cerium sulfate, cerium-3 sulfate, per 100 milliliters of water. Remember, given the density of water, 100 grams of water equals 100 milliliters of water. We're just going to make that assumption. Yes, I know it doesn't exactly hold true at all temperature ranges, but it's close enough for our purposes. I mean, imagine how much error we get in just reading this graph. I'm sure that's not even exactly 18 degrees Celsius. Okay, so for the purposes of looking at this graph, 100 grams of water is 100 milliliters of water. So we have 5 grams of cerium sulfate per 100 milliliters of water. So does that mean our answer is 5 because the graph intersected the 5? No, of course not, because we're not asking about 100 milliliters of water. We're asking about 250 milliliters of water, right? We're not asking for 100. If we have more water, clearly we can dissolve more compound before reaching the saturation point. Okay, so it turns out we have 2.5 times as much water. Therefore, we can dissolve 2.5 times as many grams of cerium sulfate. 250. I'm going to explain this in words first, and then I'm going to do it officially or systematically. 250 milliliters is 2.5 times as much water. Therefore, we can dissolve 2.5 times 5 grams in it. So that's going to be what? Well, what's 5 times 2.5? And again, even though I know the answer, I'm going to use my calculator. I've learned my lesson. 12.5 grams. So that's 12.5 grams of cerium sulfate in 250 milliliters of H2O. That's our answer. Okay, let's do it systematically now. The reading of the graph is not systematic. You just have to read the graph and know how to read a graph, know how to relate the 2 points. A graph relates 2 points on an XY axis. It relates temperature to grams of solute per 100 grams of water. So how would we actually figure this out? Well, once you read the graph, you basically have a kind of a conversion factor. We have 250 milliliters of water, and we're going to use the relationship given to us by the graph, which says that every 100 milliliters of water gives us 5 grams of cerium sulfate. That's how we read this. And that's it. Milliliters will cancel out. If you're worried about the fact that it's grams, you can always do a little density use your density of 1 gram per milliliter to convert between grams of water and milliliters of water. If that's a concern, you can add that as a step. I'm just jumping straight to milliliters because I know 100 grams of water is 100 milliliters of water. And I know that 250 milliliters of water corresponds to 250 grams of water. So the point is it's 2.5 times. 250 milliliters of water, I know from the graph, every 100 milliliters of water is equivalent to 5 grams of cerium sulfate. The line where it intersects is right between 0 and 10. So that's 5 grams of cerium sulfate. And that's it. So I have 250 divided by 100 times 5, same thing, 12.5. 12.5 grams of cerium sulfate. I don't have enough room, but you can kind of see it. So I hope all of this is making sense. You can gain a lot of information from graphs. It's a very abbreviated, shorthand way of providing you with just tables and tables of information. I mean, imagine if we had to write this out into tables for each one of these compounds, it would be a huge table. with many rows and many columns. But here you can just look at a graph and you can kind of see relationships automatically. Oh, cerium sulfate becomes less soluble with higher temperature. All the others become more. I can immediately spot points along the way that are either supersaturated or saturated, depending on which compound I'm looking at and what temperature I'm looking at. So it's very helpful and very important to be able to read graphs. It really is. All right. Oh, we have one more. I think that's the last one. Yeah. Don't worry. The next graph is just for informational purposes. We won't be using it. But here's a graph now. One more. At what temperature will my 20% potassium dichromate solution begin to recrystallize? In other words, another way of asking this question is, what is my saturation point or what is the saturation temperature for my 20% by weight potassium dichromate solution? Okay, so first let's locate potassium dichromate. It's right here, potassium dichromate. Okay, at what temperature? So this plot obviously represents the point at which something will begin to recrystallize. If it's recrystallizing, then we're assuming that we're at some point above the graph of potassium dichromate, and we are coming down to the graph. At what temperature will my 20%? We're coming down to the graph somehow, not by moving this way, but instead by moving sideways. So we started with a supersaturated solution. Oh, actually, let me put it this way. I'm sorry, I'm not explaining this well. We started with a saturated solution somewhere on a point here, and we're moving temperature-wise. The implication is that we're going from saturated at a high temperature to supersaturated at a low temperature. So at what temperature will my 20% potassium dichromate solution begin to recrystallize? So let's see. First, okay, again, I think in this case, we don't really have much of an option because we don't know exactly where we are on the graph. Let's convert. First step is going to get our 20% by weight into a comparable ratio that we can compare to the point on the graph. So my 20% means 20 grams of, what is it, potassium dichromate. I'm just going to write PD, potassium dichromate, PD for short, potassium dichromate. So that's 20 grams of potassium dichromate. What about the bottom here? Well, if it's 20%, that means it's 20 out of 100, right? So that means 20 grams of potassium dichromate plus what to get me 100? 20 divided by 100 is 20%. 20 divided by 100 times 100 equals 20%. So I have 20 grams divided by 20 plus what gives me 100 on the bottom? Clearly 80, right? That means I have 20 grams of potassium dichromate plus 80 grams of water. That would give me the equivalent, right? That much water with that much potassium dichromate times 100, that gives me my 20%, but that also gives me my ratio 20 to 80. That's what we're saying here. We're looking for a point on the graph that relates 20 grams to 80 grams. Now, the graph, unfortunately, not unfortunately, but is in 100 grams. So what do I need to do? I need to modify this. So 100 divided by 80 is going to be what? I don't know. Let me see. 100 divided by 80, that's 1 1/4. So 1.25. So if I multiply by my 80 by 1.25, I'll do the same thing to the 20. That's my factor. In other words, in order to get some kind of number or ratio that I can relate to on the graph, I'll take my 20 over 80 and I'll multiply both the top and the bottom by 1.25. Remember, if I multiply the top and the bottom by the same number, I don't change my ratio. All this does for me is it gets me a ratio of grams of solute, grams of potassium dichromate to grams of water, 100 grams of water, just like the graph is giving me information for. This whole exercise in this point is just to get my number, my 20%, in a comparable format so I can read the graph. So 20 times 1.25 is, again, I'm not even going to bother guessing or calculating. 1.25 times 20, I'm just going to use my calculator. It tells me 25. So that's 25. So now, what can I do? Now I can read the graph. 25 grams per 100 grams, that's 25 grams per 100 grams. All I do is go to my graph, look for the 25 line, which is right here, the 25 gram line right here, and I trace it all the way to potassium dichromate, and it intersects the saturation graph right here at this point. So what is that? At what temperature? That's going to be a temperature of approximately 45 degrees Celsius, and that's our answer. So I find my 25 grams, I trace it to right, or I look at that point here, I draw, why does this thing always try to get me to end the show? I trace it straight to my graph of potassium dichromate, and then I trace it straight down to see, well, what temperature do I reach that 25 grams per 100 grams saturation point for potassium dichromate? Oh, that's at 45 degrees Celsius. What does this mean? This means that I had, if my solution is just beginning to recrystallize, that means I'm coming to that temperature from a higher temperature. So because it's recrystallizing. Okay. Is there anything? I'm just trying to remember if there's anything else I wanted to say about this. No, I guess that's it. The only other thing I will mention is that technically it's not 45 degrees Celsius, but it's going to be just as soon as you get below 45 degrees Celsius. So below. Now, why do I say that? Because at 45 degrees Celsius, you'll have a saturated solution with that concentration, all of it will dissolve. So you have to get a little bit below that temperature. You have to cool it just below 45 to get it to start recrystallizing. So you sort of move a little bit to the left of that point, further down the graph, while you still have the same concentration, and immediately, I'm making kind of a mess here. Let me try that again. So if you're at this point, as soon as you start moving leftward, I didn't know, I drew these because I didn't know exactly where I was going to end up on the graph. So we're on this point here. As soon as you start moving leftward at the same concentration, but moving straight left, what happens? You end up at points that are above the saturation level. So all of these points would represent saturated. At 45, you are not saturated. All of these points represent supersaturated. Only at 45, you're at a saturated point, but at any point to the left, without decreasing the concentration, you're at supersaturation. So technically, it would have to be below 45, like 44.9 and lower. So less than 45. Instead of putting an equals, I should actually put a less than. Any temperature below 45 degrees Celsius, that's when you can expect to start seeing recrystallization, because that's the point at which you will have a supersaturated solution. 45 is the border, it's the limit. It's once you get past that limit that you reach supersaturation. That's what I wanted to say. I knew I had one more thing to mention there, and that's what I wanted to say. Okay. Okay, so hopefully all of that clarifies. Go over this, do the problems again, work through these examples again, and as you do it, you'll get used to this idea of what these graphs represent. Okay, temperature versus solubility for gases, a lot more straightforward. Gases never get more soluble with increasing temperature. It only works one way. As you raise temperature, gases become less soluble in water. I hope I'm still sharing the screen. Let me just double check that. Share, I hope so. Okay. Gases always become less, it doesn't matter the identity of the gas, and it doesn't matter what the identity of the liquid is either. It's not just water. As you raise temperature, just basic Charles's law, as you increase the temperature of a gas, its volume expands. As its volume expands, that means you have fewer gas particles per unit volume. Well, whether that unit volume is empty space or other gases or liquid, you just have less gas. So as you increase the temperature, there's going to be less gas in the water because there's going to be less gas overall everywhere that temperature takes effect. More volume also means lower density and thus lower concentration, unit of gas per unit of liquid. This actually has dire real life consequences. So as you warm up, as global warming warms up the oceans, we actually see oxygen depleted zones in both rivers, lakes, and in the ocean as well. And there's actually an article I've linked to here, Gulf hypoxia. Hypoxia, as you recall, means too little oxygen. We don't think of it, but fish and other marine life, they need oxygen to live. They breathe oxygen just like we do. They just don't breathe it through the air. They use water. They breathe it through the water. They get their oxygen, the oxygen that is dissolved. And I use the word dissolved and solubility of gases kind of in scare quotes because gases don't really dissolve in water. They don't form intermolecular attractive forces, but they inhabit the spaces in between water molecules or in between liquid molecules. So life in the ocean or life underwater needs oxygen as well. And what you get are these huge dead zones because less oxygen in the water results when you raise the temperature. Also, that oxygen doesn't penetrate deeper anymore because the warmer water floats on top, which means you don't get, the depths don't get as much oxygen as they used to. So global warming has yet another terrible consequence for life on this planet. It's robbing the oceans of oxygen. There was a balance of oxygen entering these large reservoirs of liquid, and now they are, as temperatures rise, there's less oxygen. And these create large dead zones, sometimes the size of states. So temperature versus solubility of gases. Gases always become less soluble. Unlike ionic compounds or even molecular compounds, which can go either way, sometimes they might be more soluble at higher temperatures, sometimes less. Gases only go one way because gases don't actually form intermolecular bonds, meaning they don't typically connect to liquid molecules through intermolecular forces like dipoles or anything like that. So because of that, there's really nothing holding the gases together with liquids. We've seen Henry's law before. I'll just talk about it again as a brief review. We already took a look at it in Module 12 in the gases module. As the partial pressure of a gas increases above the surface of a liquid, the greater the concentration of the gas inside the liquid. And again, that just has to do with the fact that gas particles are not stopped by liquid air interfaces. They might be slowed down. There might be less gases in the liquid than in the atmosphere, but that's not because that's only because liquid particles are more condensed. And so you have more space taken up by liquid, but the gases will go wherever they can. So when you make carbonated drinks, you pump a bunch of carbon dioxide into a sealed container. And of course, at high pressure, a lot more carbon dioxide will enter the liquid as well as sitting on top of the liquid in the space provided. So the partial pressure of CO2 in our atmosphere is less than 0.1 atmospheres. So we don't see much CO2 in liquids naturally, but if you artificially increase the amount of CO2 by pumping in a bunch of carbon dioxide on top of a liquid, by compressing that space or just by filling that space with more CO2, you'll get a lot more CO2 in the water. As more carbon dioxide is produced in our atmosphere, and again, that's one of our major greenhouse gases, CO2, the oceans are becoming more acidified, and this is destroying coral reefs. They start to turn white, they lose their color. Basically, this is because of the acid that gets produced. As more carbon dioxide enters the oceans, you get this, you start to generate more carbonic acid. Remember, the interaction of carbonic acid between its various different either decomposing or dissociations, it's all equilibrium based. It's all reversible. So the more CO2 you put into water, the more carbonic acid you get. The more carbonic acid you get, the more of that acid will dissociate in the water. Instead of decomposing to produce CO2 and leave, instead you'll get this equilibrium shifting toward producing more acid, more proton, more hydrogen ions in the water. You get more acid in the water, and the acid actually dissolves the limestone that most creatures, well, not fish, but a lot of creatures like shell creatures, shell life, whatever you want to call it. They build their houses out of limestone, which is a base, hydroxide, and that will react with the acid from carbonic acid, and it will dissolve into water. And coral reefs also are made of a lot of limestone, and so the acid reacts with them, and it basically just wears away those coral reefs, as well as other, and those are just sort of anchor points for a lot of different ecological systems underwater. So in addition to the harm it does to clams, cephalopods, and other kinds of, crabs and other kinds of creatures like that, it also harms coral reefs, which are basically just large living systems. So that's yet another way. This is another separate way that increased greenhouse gases. In addition to the warming, the gas itself actually causes direct problems through the acidification of our waters. Not enough to harm us. I mean, it's not a matter of, you drink acid water and you melt, and it doesn't work that way. It's a subtle difference, but it does, changing the pH of the oceans and of water in general, fresh water, destroys the delicate balance that exists for the life that lives in that water. pH is a measure of acidity, which we'll talk about in the next module, acids and bases. Okay, another type of solution are electrolyte solutions. Electrolytes are solutions that can conduct an electrical current. Any solution containing dissolved ions, and they must be ions. You must have ions that are dissolved in solution to get an electrolyte solution. Any solution containing dissolved ions will be an electrolyte solution. If you have an ionic compound that doesn't dissolve in water, you are not going to get an electrolyte solution by just sticking it in the water, right? You can't just take, for example, calcium carbonate, which doesn't dissolve in water, stick it into the water and get a current to flow through that water. That doesn't work that way. The ions actually have to dissolve. They actually have to be separated from their solid state and in the aqueous state. A non-electrolyte solution is one that contains no dissolved ions. Usually, these are, well, actually not usually, these are always molecular solutes dissolved in water, for example. A molecular solute, other than acids, all other molecular compounds do not produce ions when they dissolve in water. They do not dissolve through dissociation. They dissolve through the formation of intermolecular bonds, so-called bonds. One molecule will separate from other molecules and be dispersed throughout the water, but they will not produce ions. Molecules do not break down to give you ions, except for acids. Acids are a special case. There are only two types of compounds, and here I'm just going to say that. There are only two types of compounds that can act as electrolytes: soluble ionic compounds and acids. Remember, acids are molecules that behave very much like ionic compounds when they are in water. Ions in solution act as charge carriers. This is why it takes ions, because they are positives and negatives. And an electrical current is nothing more than the flow of negative charge and positive charge in opposite directions. The positive ions migrate to one electrode, negative ions migrate to the opposite electrode, the opposite charge electrode in an electrolyte solution. And here, let's look at a picture. Pictures actually help a lot here. So pictured below is a basic chemical cell. Terminology: cathode. Cathode is the negatively charged potential electrode. So for example, this would be your cathode. It has a negative charge. This is plugged into a wall outlet. The wall outlet provides voltage. It provides a difference in electrical potential energy, not active energy. It's not a current, it's not an electrical current until there's actually a flow of electrons from one electrode to the other. Until then, they're just potentials, they're voltages. It's a voltage difference between the negative and the positive. So when you plug something in, you get a voltage difference, but you don't get any current unless the circuit is complete, meaning unless there's something to connect the negative potential air zone to the positive, or the negative cathode to the positive cathode. The negative electrode to the positive electrode, the cathode to the anode. So the cathode is the negative, the anode is the positive. That might actually be reversed in other countries. That's just a convention that we use in America. I think Britain has them in reverse, or the United Kingdom, whatever you want to call it. And certain other countries might also be different, just like driving on the road, left versus right. So an electrical current is nothing more, I already said, the flow of charge. Now, if there are no particles that can that can put into effect the flow of charge, then there is no conductivity. There is no electrical flow. So for example, ethanol. Ethanol, I hope you know by now, is a molecular compound. It's an alcohol. It's the alcohol that people drink. Ethanol is a molecule. So when you dissolve ethanol in water, it dissolves very well, but it does not dissociate. It dissolves, but not by dissociating. It simply dissolves by creating intermolecular hydrogen bonds with water. So these ethanol molecule, I don't know why they drew them as two spheres. There would only be one sphere, right? They don't dissolve into ions, so there is no electrical current to be, there's nothing to sort of conduct the charge from one electrode to another. Look at potassium chloride. Here you have high conductivity. Potassium chloride would be an electrolyte solution. It would conduct an electrical current. The positive potassium ions are free to flow toward the cathode, toward the negatively charged electrode. Electrode is the general term. Cathode and anode are specifically referring to the charge of a particular electrode. So the potassium ions will flow in the solution, they will flow over to the negative electrode, and the chloride ions, which are negative, will flow over to the positive electrode, thus creating a flow of charge. And that is all that an electrical current is. It's a flow of charge. It's not even necessarily a flow of negative charge. It doesn't matter, because if negative charge is flowing in one direction, positive charge is flowing in the opposite direction. So you can see it as either a flow of electrons in one direction, or the flow of the lack of electrons, what are called the holes, H-O-L-E, flowing, the holes, the positive charges, the holes that are left behind by the electrons leaving, they're called holes, positive holes. You can see it as the flow of holes in the opposite direction of the electrons. So holes flow, say, for example, from left to right in this example, and electrons flow from, wait a minute, did I have this right? No, I'm sorry. The electrons flow from left to right in this picture. Electrons flow left to right. Holes flow from right to left. The emptiness, the lack of electrons. So you can see it that way. Acetic acid, I want you to remember this among other things, but for the remainder of our discussion, I want you to remember that acetic acid, HC2H3O2, is a weak acid, and therefore also a weak electrolyte, or its for solutions of acetic acid form weak electrolytes. Remember, acetic acid is nothing more than hydrogen acetate. Acetic acid. If you want to remember, if you need a reminder, acetic acid, HC2H3O2, hydrogen acetate, or a more structurally honest way to write it would be this. Either one of these representations is completely correct. Remember, if there is an acid, I'll generally write it with the hydrogen up front so that you remember that it's an acid. So, but I didn't do that later on. I think I wrote it this way instead. But either way, this is acetic acid. Acetic acid is a weak acid, and all weak acids are weak electrolytes. What does that mean exactly? Look at the bulb. A weak electrolyte produces a dim bulb. A strong electrolyte will produce a bright bulb, a brightly lit bulb. And a non-electrolyte, no current. So no bulb, well, no light coming from the bulb. The bulb remains off because the circuit is not completed, meaning there is no connection between the two electrodes. You have, in order for electricity to flow, it must have an uninterrupted, unbroken path to make a circuit, a so-called circuit, meaning negative charge flowing through one place, across, and then to the other place, and make a complete circuit. A circuit just means you go completely around, and that's how electricity flows. If there is a break anywhere in the circuit, electricity stops flowing everywhere, no matter how far away that break is. And so in this case, the break occurs in the solution. The solution, because it's not an electrolyte solution, does not act as a conduit for charge. So the circuit gets broken right there. Here, though, the solution acts as a continuation of the circuit. In other words, an electrolyte is very much like a wire. It acts like a wire. It will conduct that electrical current, just like a metallic compound will conduct an electrical current. All because it has ions that are free to move back and forth between the electrodes. So that's an electrolyte solution. Soluble ionic compounds and acids are strong electrolytes. Weak acids and weakly soluble or not completely soluble ionic compounds are called weak electrolytes, and insoluble ionic compounds and molecular compounds are non-electrolytes. Oh, okay, so I already talked about this. So just for example, a strong electrolyte, those compounds that dissociate 100%, meaning whatever amount of, whatever your Van't Hoff factor is, that's the multiple you multiply the concentration by to get your concentration of dissolved ions. So for example, aluminum chloride is a strong electrolyte, meaning if you have a 1 molar solution of aluminum chloride, you will have effectively 4 moles of ions per liter, or in other words, a 4 molar solution of ions. It doesn't matter if they're positive or, well, obviously you're going to have an equal number of positive and negative charges, even if not an equal number of ions themselves. So you'll get 4 molar concentration of ions. That's the Van't Hoff factor at work. So 1 molar aluminum chloride gives you exactly 4 molar ions because every single one of these chlorides separates out. And so you get 3 chlorides, plus you get an aluminum, plus 1 aluminum. So that's 4 ions per mole of aluminum chloride. What is the molarity of ions? So here's a little self-check for you. What is the molarity of ions in solution in a 0.6 molar sodium chloride solution? You have a 0.6 molar sodium chloride solution. Sodium chloride is definitely a strong electrolyte. So what is the molarity of ion in terms of ions, not in terms, whenever we see a reported molarity, it is per formula unit, per Na and Cl together as 1 unit. But what is the molarity if we wanted to express it in terms of the number of ions, the moles of ions per liter of solution? How many? Well, we have, I mean, pause the video now if you want to think of it on your own. Here it comes. Okay, so we have 2 ions per formula unit, right? We have NaCl. We have a sodium ion. We have 1 sodium ion, and we've done this before, plus 1 chloride ion. That's a total of 2 ions. So we have 2 times 0.6. Our Van't Hoff factor I is equal to 2. And so we have 2 times 0.6. That's going to be 1.2 molar of ions. In other words, we have 1.2 moles of ions for every 1 liter of this solution. If we have half a liter, we have 0.6 mole. If we have a quarter of a liter, we have 0.3 molar or 0.3 moles of ions. In other words, with strong electrolytes, you get exactly the number of ions you would predict from just looking at the formula and breaking it up into its component ions. Now, a weak electrolyte is a little bit tricky because you don't actually get a 1-to-1 ratio of the ions that you would expect. That's because weak electrolytes, which are mostly just what are called weak acids, like hydrofluoric acid here is a weak acid, as are a few other acids. Because it's a weak electrolyte and thus a weak acid as well. By the way, a weak acid is a weak electrolyte by definition. But not all weak electrolytes are weak acids. There are many other weak electrolytes that are not acids, like partially soluble ionic compounds. Okay, so anyway, so this weak acid, hydrofluoric acid, if we have 1 molar of hydrofluoric acid, we are not actually going to get 2 molar of ions. That's because the hydrofluoric acid does not have a very good tendency to dissociate. It dissolves fine in water, but it doesn't dissociate very well. In fact, less than 1% of the hydrofluoric acid will actually dissociate into ions. So every 1 molar of hydrofluoric or hydrogen fluoride that enters the water, you're going to get like less than 0.001 or 0.002. In my example here, this isn't actually the value, but just as an example, you're going to get 0.002 molar solution of ions, much less than 1%. Why is that? Because it's just not a very good dissociator. The hydrogen and the fluorine like to stick together, even in the water. The water's dipole is strong enough to pull apart some of the hydrogen from the fluoride, but not most of it, just a little bit of it. So weak electrolytes have a tendency not to dissociate as much as you would think so. Their Van 't Hoff factor tends to be less than 1. Less than 1. Well, actually, no, I shouldn't say less than 1. Less than, how do I say this? In terms of ions, I guess it would be less than the fraction, it would be a fractional amount. But in terms of total dissolved compound, I shouldn't say less than 1. It would be slightly above 1. It would be between 1 and 2, much less than 2, closer to 1. Let's put it that way, a little bit over 1, like 1.0001, something like that. The Van 't Hoff factor would be close to 1, maybe slightly above, but not by much. So the difference between a strong electrolyte and a weak electrolyte is the degree to which the compound dissociates in solution, dissociates to produce ions. Remember that, to produce ions. Some compounds that can produce ions just don't produce as many of them as you would expect from looking at the formula because they just stick together better. The molecule or the ionic compound just doesn't want to break down or dissociate very much. Weak acids and bases are electrolytes. I want you to, or weak electrolytes. I want you to remember this. In the next module, when we talk about acids and bases, we're going to make a big fuss about the distinction between weak acids and strong acids, and weak bases and strong bases. And I'm going to give you a particular specific list of strong acids and strong bases to remember. And you'll, outside of that list, every other acid and base will be automatically presumed to be weak. But I'll tell you right now, in addition to acetic acid, any acid, anything that starts with an H and has carbon, any acid that has carbon in its formula is weak. And I've said this before, and you probably remember that, but any carbon-containing acid is weak. It's a weak acid and therefore must be a weak electrolyte. By definition, all weak acids are weak electrolytes. But not all weak electrolytes are weak acids. There are other kinds of weak electrolytes. But all weak acids behave as weak electrolytes in solution. Now, there's one other thing I want to mention, but I'll mention it in the course of looking over our example here. Because there's one other point, a couple of points I want to make. Okay, label each one of these as either a strong electrolyte, a weak electrolyte, or a non-electrolyte. So in order to do this, you're going to have to go through and figure out, first of all, are you looking at an ionic compound or a molecular compound? Looking at the formula, of course, you should be able to tell. But then to distinguish between a weak or a strong, you're going to actually have to have some knowledge, meaning you're going to have to know some information about the world of, well, specifically weak acids versus strong acids, and weak bases versus strong bases. So for that reason, I actually told you what you needed to know in this list. But after this mod, when we look at weak acids and strong, when we go into acids and bases, you will actually know. You'll be able to answer these questions a little bit better. Okay, so first one, ammonium sulfate. Now, though there are no metals in this molecule, in this compound, we still know that this is what? An ionic compound, right? We still know that this is ionic. How do we know? Because ammonium is a positive ion, sulfate is a negative ion. Therefore, this is an ionic compound. And we know that all ammonium compounds are soluble. So for our purposes, we're just going to assume that anything that makes the soluble list must be very good at being soluble, and therefore this is going to be a strong electrolyte. Strong electrolyte because all ammonium compounds are soluble in water. You know this is in water, by the way, because I put the physical state or phase designation as aqueous, means specifically dissolved in water. So ionic compound that dissolves well in water, strong electrolyte. Next one, we have phosphorus trichloride, aqueous. So this phosphorus trichloride is also dissolved in water. So this is an aqueous solution. Is this a strong electrolyte, a weak electrolyte, or a non-electrolyte? Maybe you should just pause the video at this point, work through it yourself, and then, we'll go through it together. Okay, I assume you're back. Okay, PCl3, aqueous. It is aqueous, but does that mean it dissolved? It dissolves fine, but does it dissociate? No, this is not an ionic compound. This is a polar covalent compound, right? This is a molecule. It's a molecular compound, i.e., a molecule. Well, molecules don't dissociate into ions. So this is a non-electrolyte. Molecules are not going to, plain old molecules that are not acids are not going to produce ions when they dissolve. They can dissolve, but they don't dissociate. Remember, you do not break up molecules into their individual atoms. That would be a huge mistake. These are covalent bonds. Water cannot break a covalent bond, except between oxygen and hydrogen for some reason. But that's only because of that special sort of dipole thing. But that's a unique circumstance. How about the next one? Again, what kind of compound do we have here? Again, it's molecular. The fact that it dissolves in water does not mean it's automatically going to dissociate. It dissolves without dissociating. Molecules can dissolve without dissociating. Ionic compounds, on the other hand, can only dissolve through dissociation. So this, again, is going to be a non-electrolyte. How about liquid bromine? Now, this one is a very strange one. And I don't blame you if you don't know yet what that means. Liquid bromine, it's a pure liquid. Bromine, as you recall, is a diatomic molecule. So you have these liquid bromine molecules just sort of floating around with each other. It's a very non-polar molecule, but non-polar molecule indicates what? Well, here's another thing. There's no water. Even if somehow this had been some sort of conductive material in the liquid state, or an ionic compound somehow in the liquid state, like liquid sodium chloride, it still wouldn't conduct, right? Because overall, it's in the liquid phase. There's no water. There is no dissociation. Even if this could, it can't, but even if it could dissociate into ions, the fact that it's in the liquid state, not aqueous, means you don't have any ions that are free to travel from one place to another. So this is definitely a non-electrolyte. In fact, anything in the liquid state or the solid state is not going to be an electrolyte, because you actually have to have the ions dissociated in water, free to move through the water in solution to go from one electrode to another or to arrive at an electrode. The liquid state is a little bit different. Even molten sodium chloride, even liquefied sodium chloride wouldn't serve. I don't believe it would serve as an electrolyte. I could be wrong about this though. But I believe that what will end, at least not a very good one or not a very effective one, because the sodium ions and the chloride ions in the liquid state are still going to hold on to each other. So it would be I think it would be a very poor conductor of an electrical current, because you'd have to essentially reduce your sodium ions to sodium metal and oxidize your chloride into chlorine gas. And I have a feeling that would be very difficult, practically speaking, very difficult to do. So I don't believe that would actually work either. Despite the fact that sodium chloride is made up of positive and negative ions, not having it in aqueous physical state would actually make this very unlikely to be a very good electrolyte. So it has to be aqueous solution. How about pure water? Does pure water have any dissolved ions? No, by definition, pure water is just H2O. In other words, this is another liquid state. So anything in the liquid state, just go ahead and automatically assume no electrolyte. Pure water is not going to be a solution. It has no dissolved ions. Therefore, it is a non-electrolyte. How about solid magnesium oxide? Now, magnesium oxide is definitely an ionic compound. You've got magnesium 2+ and you've got oxide 2-. You've got your ions, but this is in the solid state. Remember what the solid state looked like? The solid state was just a bunch of ions locked together, rigidly held in fixed positions. So here are your oxides, and then you have your magnesium ions in the interstitial spaces in between those oxides. You have this rigid lattice. So how on earth is this going to do anything? It's not. This is also going to be a non-electrolyte. Solids do not, solids do not act as electrolytes. Now you can have a solid metal, of course, will act as a good electrical conductor, but we're not talking about electrical conductivity in the abstract here. We're talking specifically about electrolytes, about compounds that can use their ions to transfer charge from one electrode to another. We're not talking about wires. That would be trivially obvious. Yes, metal wires conduct electrical current. Those aren't electrolytes. We're talking about things that specifically use their own ions to transfer charge instead of just transferring electrons from one place to another. So solid magnesium oxide won't work. Now, if you were able to dissolve magnesium oxide in water, and it's not really that soluble, but if you were, actually what would happen is the magnesium oxide would react with the water to get magnesium hydroxide, which has some limited solubility in water. You would actually end up with a weak electrolyte because magnesium hydroxide is lightly soluble in water. You get a little bit of dissolution from magnesium hydroxide. So you could get a little bit, but this is in the solid state. No solution, no electrolyte. Basically, that's it. No solution, no electrolyte. Liquid state, solid state, gaseous state, even worse. No electrolyte. It must be aqueous. And if it's aqueous, it must be an ionic compound or an acid. Now, the last one here, acetic acid, I am telling you right now, is a weak acid, but I want you to remember that. Acetic acid is a weak acid. All weak acids are weak electrolytes. So this is definitely a weak electrolyte. It's the only example of a weak electrolyte. Right now, it's the only example I can give you because we haven't talked about acids and bases or about weak acids and weak bases. And so far as solubility goes, we've only really kind of drawn a binary between something's either soluble, an ionic compound's either soluble or insoluble. The truth is there are partially soluble ionic compounds out there like magnesium hydroxide or even beryllium hydroxide. There are ionic compounds that will dissolve a little bit, but not a lot. Okay, so that's the idea behind electrolytes. You're basically looking for soluble ionic compounds or acids. Now, another way to categorize mixtures. Now, these are not going to be solutions. In fact, I left this to the end specifically to distinguish these heterogeneous mixtures called colloids and suspensions from true solutions. In fact, we're going to see that we are going to compare them to solutions in the way that they differ or are similar to true solutions, but these are not true solutions. True solutions have particles that are dissolved in a solvent. These are too small, too big of particles, and they are not truly dissolved. Okay, so the separation between colloid mixtures and what are called suspension mixtures, suspensions versus colloids, has to do with particle size mainly, but there are other differentiating characteristics as well. So let's talk about the characteristics of each one. We'll look at some examples, and that'll mainly be it. But again, keep in mind, these are not solutions. We are distinguishing between true solutions and these non-dissolved, dispersed particles. By the way, we refer to these as being in the dispersed phase. That's yet another phase. Don't worry, I don't harp on this too much, but I just want to let you know that the terminology associated with colloids and suspensions is they're called the dispersed phase. And I'll write this in the bottom. For some reason, I don't think I really made a big mention of it in these PowerPoints. The dispersed phase. To distinguish from aqueous, aqueous means something dissolved in water. But in this case, this is dispersed. Basically, it just means that these particles are spread out, or at least temporarily spread out, if not permanently spread out, but they are not truly dissolved. They're not aqueous, or whatever the solvent happens to be. Okay, so colloids. Colloids are definitely the smaller of the two. They are too small. The particles in a colloidal dispersion, that's another part of the terminology. In a colloidal dispersion, the particles are too small to be seen with the naked eye, but the effects can be observed. By the way, because of this, it's actually hard to tell. Sometimes it's hard to tell with the naked eye whether you're looking at a true solution or a colloid. If the colloid particles are too small and they're too hard to distinguish, you may actually think you've got a true solution. But there is one way to distinguish, and that is through the Tyndall effect. The Tyndall effect can actually discern between colloids and solutions. A true solution, in a solution, the dissolved particles are at the atomic or the molecular level. That's how small the dissolved particles are. They're the size of atoms and molecules, incredibly small. We're talking about just a few hundred picometers. When you shine a light into a solution, the light will refract, meaning it'll bend, but it will not scatter. It will not scatter. Scatter, believe it or not, is an official term. It's a real term. It refers to light scattering in all directions, being deflected or reflected or actually I should say re-emitted in all directions. That is the scattering of light. Only dispersed particles, only colloidal particles will scatter light. Dissolved particles are not big enough to scatter light. So if you shine a light through a solution, the light goes straight through, or maybe it refracts, it bends at a constant, consistent, predictable, known angle, but it is coherent. Colloids, on the other hand, they might look like solutions, but as soon as you turn on that light, you get a sort of headlights in the fog kind of effect. You get a scattering of light. The light just becomes a giant blur. So that's the Tyndall effect. That's how you shine a light through your suspected colloidal dispersion. And if the light scatters, you've got yourself a colloid. If the light just goes through in a coherent beam, in one end, out the other, same beam, then you know it's a true solution. Particles, another thing about colloids, the particles don't separate out over time. Now, in this respect, they are very much like solutions. And that's one of the things that might be able to fool you, which is why you might have to turn to the Tyndall effect and test it that way. But particles don't separate out over time under normal conditions, though very fast centrifugation can force the particles to settle out. Remember what a centrifuge does. It spins samples around really, really fast. So fast that you generate a sort of artificial G-force, gravitational force, which will pull down even the slightest difference in density, will pull down the more dense particles to the bottom of your vial or test tube or whatever vessel you choose to load into your centrifuge. Usually they're thin tubes. So under extremely fast, powerful centrifugation, you will see colloids separate out. Whereas in a true solution, No amount of spinning will ever separate a dissolved particle from its solvent, because they are connected to each other through intermolecular forces that are too strong to overcome that way. Okay, the particles can't be filtered out. Again, this is very similar to solutions. A colloid is almost a solution. It's just missing it by particle size. That's about it. Particles cannot be filtered out. Typically, colloidal dispersions can't be filtered out. However, there are such things as molecular sieves, molecule-sized filters, or pores in the filters that can do the job. But for the most part, a typical filter will not be able to filter out colloidal dispersions. Now, the particle size is really the big differentiating factor here. Particle sizes are from 1 nanometer, which is, thousands of picometers, well, actually 1,000 picometers, to 0.1 or 1/10 of a micron or micrometer. Micrometer, micron. Just FYI, remember, I mentioned this before, but this is a micron is another way of referring to the word micrometer. Instead of saying micrometer, most people will say micron, but just be aware, they really mean the same thing, micron and micrometer. So 1/10 of a micrometer. So particle sizes can be visible to the naked eye. The limit to human vision is around the 1/10 of a micron level. So, the width, like a fraction of a width of a hair is about that level. Nanoparticles fall into this range. Nanoparticles, have you ever heard of nanotechnology or nanoparticles? They are usually particles made up of thousands, if not tens of thousands of atoms. So examples of colloids: grit particles for polishing. You have nanoparticles, or you have colloidal suspensions inside of toothpaste. You have little tiny grit. That means little hard pieces or little chunks. Of course, when I say chunks, I mean on the nanometer level or multi-nanometer level of chunks. So you won't notice. To you, toothpaste feels like a completely liquidy, pasty sort of thing, but really, there are tiny particles there. And the reason they're there is to mechanically disrupt the plaque that forms on your gums and teeth. Bacteria form very tough outer layers. They encase themselves in sugars that basically protect them from the outside world. So the only way to disrupt those plaques, those sort of domes that bacteria create around themselves and around their communities, is to mechanically go in with little sharp-edged particles and disrupt them, mechanically scraping them out. Pure liquid will not do it. So grit in polishing and toothpaste, the grit in toothpaste for scrubbing away plaque through sheer mechanical force. Air dispersed in liquid is another example of colloids. The air trapped inside of foam or whipped cream or shaving foam is an example of a colloid. Fog is a great example of a colloid. That's a liquid dispersed in air. Now, given time, fog particles, the liquid particles, will eventually settle out. They will eventually fall to the earth. But for a long time, the particles are so small, they will hover in the air. And this is and when you turn your high beams on, and you're not supposed to do this, but don't turn your high beams on in the fog. Why? Because that's when you get the Tyndall effect. Your high beams are going to scatter. The light coming from your high beams will be scattered by the fog, which is just one big colloid. So when you're driving the fog, just be aware you're driving through a colloidal dispersion. And so if you turn on your high beams, that light is going to scatter and you're not going to see anything. That is the Tyndall effect in real life. It happens at the macro level, at the everyday object level. So fog is a great example of a colloid, and turning on your lights in the fog. That's why oftentimes you don't even necessarily know there is fog until you turn on the lights or until you come upon a street light at night or early in the morning when there's fog. You don't even notice the fog until you see the light scatter from either your headlights or lamps overhead. That's the Tyndall effect. These are more colloids found in everyday life. Milk, for example, is you've got tiny little micelles, little drops of casein, which is proteins in the milk. You also have little droplets of fat, oil. So you've got a liquid in liquid colloid in milk. Butter, you've got fine oil drop. Butter is basically just fats suspended in water. I don't know if you knew this, but butter is there's a big chunk of butter that is just pure water. Butter differs in terms of its moisture content, but it is a mixture of water and fat emulsified together. Paints also contain fine, again, very tiny particles dispersed among a liquid. That's how you get paint. Believe it or not, the paint is not a liquid. It's not even a solution. It's actually a dispersed, the pigments are generally solids dispersed in a liquid. And any kind of lotion or beauty cream or cosmetic is also, just like paint, just like cosmetics, just like paint for the face, right? Same idea, you've got a dispersed medium of solids in liquids. Chocolate even is cocoa butter particles in water or milk. Strange as it may seem. In fact, if you've ever had matcha tea, matcha green tea, matcha powder never actually dissolves, and neither do most of the powders that they put in blended drinks. That powder does not dissolve in milk or water. You actually have a fine dispersal of a colloid. So a frappuccino is generally a colloid, a frappuccino or a blended coffee drink or some kind of drink. Actually, technically, a milkshake is also a colloid, but it's a liquid colloid, whereas blended drinks with powders tend to be solid and liquid colloids. Okay. Suspensions. Suspensions have much larger particles. In fact, that's the reason why I put this here. The preeminent example of a really sort of obvious suspension are lava lamps. See these lava lamps? Those globules there, I'm not sure exactly. I think they're globules of oil with food coloring in them or something. I'm not really sure how it works with the coloring, but these globules of oil or whatever they are floating in the water, those are suspended particles. Suspended particles are visible to the naked eye. They're huge. They're easily filtered out because the particles are so large. The dispersed particles can be filtered. Unlike colloids, there's absolutely no confusing a suspension for a solution. It's very obvious. As soon as you see a suspension, you know it's a suspension, because unlike colloids, which may be opaque, may be cloudy, may be clear, suspensions are always cloudy and usually completely opaque. They are completely non-see-through. They don't scatter light because they block light. They actually will absorb or reflect light. So you shine light through try to shine light through a suspension, you're not going to see any light coming out the other end. Instead, they're just going to block the light completely. They block light. There's no test necessary because there's no confusing a suspension for a solution. So lava lamps, obviously. Chocolate chip cookies, by the way, are also examples of a solid and solid suspension. You have chocolate chips suspended in another solid. Muddy water, where you can see dirt particles arising in the water. Another thing to distinguish a suspension from a colloid or a solution, a suspension, the particles are large enough that their dispersal is only temporary. Given time, given a relatively short period of time, the dispersed phase, the suspended particles, will settle out of solution, out of so-called solution, not even solution. They will settle out of the mixture and they will form a sediment on the bottom. In other words, sedimentation. All the solid particle in a liquid will settle to the bottom and form a layer of solid, showing that it was never truly a solution. It's not even a homogeneous mixture, it's a heterogeneous mixture. Muddy water, orange juice with pulp. The pulp, of course, is your suspended particle. Blood is an example. You have all these cells dispersed in the plasma, the liquid, the pure liquid part of blood. Any liquid that you have to shake before drinking is a suspension. So for example, if you buy soy milk, you usually have to shake the soy milk before you drink it. That's because you want all that wonderful vitamin B12 and other vitamins inside your soy milk. Also, antibiotics. Here are just two, erythromycin and penicillin. Both of these are antibiotics, and they also, you can kind of see the top is sort of clear, but the bottom is white and opaque. Same thing here. The bottom is white. You've got these powdery stuff, this powdery stuff at the bottom. You've got clear solution on top. Also, antacids are like this. They are suspensions. You have to shake them before you use them. Otherwise, all the good stuff remains at the bottom of your bottle, and you don't get any. So anything you got to shake before take, if you shake it before you take it, it's a suspension. So whether it's antacids or penicillin or some kind of antibiotic or a frappuccino or some sort of matcha tea drink. You have to shake it to get the full benefit or to get the full flavor. It's a suspension. Suspended particles eventually settle out on their own without too much coaxing from the outside. You don't need a centrifuge to do it. Just give it a little bit of time and it happens on its own. Now, if you are in a rush, blood typically gets put into a centrifuge to separate the plasma from the the hemoglobin and all the red blood cells and everything else, all the other types of cells. But that's the patience. Eventually it settles out on its own anyway. So suspensions. Again, colloids and suspensions are not solutions. They're simply mixtures. They are distinct from solutions. They are not truly dissolved. And that's mainly it. Yeah, that is module 13. That was the last thing I had to say about module 13, which is the talks about solutions. Now, of course, I ended with things that aren't truly solutions, but these are mixtures that are common enough that they were worth talking about in the context of mixtures, even if they're not actual solutions. I hope all that was informative. I especially hope the part with the solubility versus temperature graphs back here. You know, if you didn't understand it, go over it again, through it slowly, take it one step at a time, get to know these graphs, get to understand it's not just for this topic, but in general, science makes heavy use of graphs and presenting information in graphical form. So knowing if you can read this, you can read pretty much any graph. If you understand all, the way I navigated this in this lecture, the way I navigated these graphs, then that's going to be a real advantage for you in understanding scientific data in general. Of course, not all scientific data uses the same concepts in a graph, but if you can navigate your way around what the graph means, what the points above the graph, below the graph, to the left of the graph, to the right of the graph, to the right of the curve, what they all mean, and how the variables that are in the graph are related, whether they're directly proportional with a positive slope or inversely proportional with a negative slope. If you understand all that, that's a real, then you've got that covered as far as your scientific literacy. And that's my goal for you, is to be scientifically literate. Okay, I hope all of that was helpful and informative and enjoyable. Let me know how it's going with you. Let me know how, if you have any questions or comments or concerns, if you spot any mistakes, please let me know. And I will see you in the next video. Take care, everyone.